Hey, my name is Shannon Lorio, and today I will walk through an introduction to the theory behind the LI-6400, 6400 XT. We'll go through kind of the principles behind the instrument. It will be very brief. We have additional videos that go into more detail on the measurements themselves, but we think it's important that you understand the basics of the theory before we get started. So a good place to start when we talk about the theory behind the LI-6400 and 6400 XT is to show a basic review of photosynthesis. As we know, photosynthesis is made up of the light reactions and the light independent reactions. We can assess the electron transport rate in the light reactions by using chlorophyll fluorescence. And we can estimate or actually measure the rate of CO2 fixation in the light independent reactions. So how do we do that? Well, let's start with gas exchange. We know that on the surface of leaves there are pores that are called stomates. Stoma is plural. And through the stoma, they control the movement of CO2 into the leaf and water vapor out of the leaf. So one of the parameters that is interesting to researchers is to actually measure what that stomatal conductance is, how open those stomates are and how many there are. So we can use our infrared gas analyzers to actually measure the amount of CO2 going into the leaf and the amount of water vapor leaving the leaf. And that is done through a mass balance equation. Basically, we take a leaf and we put it in the chamber, and assuming the conditions are right, that leaf is assimilating CO2 and transpiring water vapor. We can measure those two processes by knowing the flow rate of air entering the chamber, as well as the CO2 and water vapor concentrations in that airstream, and also the flow rate and CO2 and water vapor concentrations leaving the chamber. And we can develop a basic mass balance. So leaf area, transpiration, flow, and water vapor concentrations in and out of the chamber. And we can do that for both transpiration and for carbon assimilation. If we look at the units, transpiration is then calculated as, again, our flow rate is measured in moles per second, our water vapor is measured in millimoles per mole, our leaf area is entered into the 6400 as a centimeter squared area, and then we have a conversion to turn it into meter squared. But you can see the moles cancel out, and we're left with millimoles of water vapor per meter squared in second. We can do a similar expression for carbon assimilation. Again, flow is measured in moles per second. CO2 is measured in micromoles of CO2 per mole of air. And again, we have the leaf area term. Moles cancel out, and we're left with micromoles of CO2 per meter squared in second. So if we return to actually how we do this in the instrument, it may be easiest to think of a traditional open system where we bring air in from the room, we measure the CO2 and water vapor concentration in that air, we measure the flow rate, and then we move that air into and out of a cuvette, and then back through another analyzer to measure the CO2 and water vapor concentration. And then we return that air to the room. So it is a flow-through system. We have air entering and leaving. And again, if we remember that expression we talked about earlier, photosynthesis is basically the flow rate times the delta CO2, the difference measured between the reference and the sample, divided by the area of the leaf in the chamber. Transpiration is a similar expression. The 6400 operates with this basic premise. However, a key difference in the 6400 is that the reference and sample analyzers are not located in the console. They are located up in the sensor head, and in fact the sample analyzer is located within the mixing volume of the leaf, which ensures that we get real-time measurements of our photosynthesis and transpiration rates. There are no delays. We also avoid problems that happen if you have tubing between your cuvette and your analyzer. That tubing can contribute absorption and desorption properties that can affect the rates that you're trying to measure, and we avoid all that by the design of the instrument. So the actual carbon assimilation expression used in the instrument is a little more complex, and the reason that is we also account for dilution. So as water vapor is transpired into the cuvette, it actually is diluting some of the CO2 concentration, and so we account for that in our carbon assimilation calculation. So here's the basic flow path. Again, we have a console and we have a sensor head. So you can kind of think of the console as your air conditioning unit, and the sensor head is where your analyzers and your leaf chamber are located. Again, the air is brought in, it's conditioned by our CO2 scrub, our pure CO2, our desiccant. It's mixed inside. We have a pump that controls the flow of air through the system. We have a separate flow rate controller, and this is achieved so that we can keep the pump at a constant speed. And what we've seen with that design is that our pumps actually last a very long time. This flow rate controller then allows us to control the amount of flow going to our sample chamber. The extra flow that we don't want ends up joining to our reference analyzer. Just before our sample analyzer airstream leaves the console, we have a mass flow meter that measures our flow rate. Then both airstreams for the reference and sample go up to the sensor head. They are measured by the analyzers and then exhausted out to the room. This is the way the air is mixed in our leaf chamber. There is a design where the central hole is under a slight negative pressure and the outer holes are under a positive pressure, and so we have a pushing and pulling that happens, and you can see that that happens on both the lower chamber as well as the upper chamber of the leaf. And if you look at your chamber installed on your instrument and open up the chamber, you will likely be able to see those three holes as well as this air channel at the back that allows for this mixing. Very, very efficient, very high boundary layer conductance with this design. So how do the analyzers actually measure CO2 and water vapor concentration? Well, these are infrared gas analyzers. So we take advantage of the infrared absorption spectra where CO2 and water vapor absorbs, and we can see there's a very strong peak here for CO2, and if we can measure the amount of light received in that peak versus the amount of light received in a peak just before, we can actually measure the amount of CO2 concentration in the airstream. We do the same thing for water vapor. We measure the amount of infrared light absorbed in that band versus a band very close but not in the same absorbing band. And from that we can calculate the amount of water vapor in the airstream. So we have a filter wheel design that looks something like this, where we have our CO2 absorbing and reference, water absorbing and water reference. So this filter sits in front of the detector that you can see here, and with phase lock loop technology we know at any one time which filter is in front of the detector, and this filter wheel turns at 300 times a second, so very, very fast. We're taking very fast measurements of CO2 and water vapor, and The nice part about having the reference scheme, the absorbing and the reference scheme, is that if we have any dirt or debris that gets into our analyzer, the reference, that dirt or debris can scatter the infrared light, making it look like there's more CO2 or water vapor than there actually is. But by having the reference band in there, we actually subtract out that scattering. So we look at the difference between the absorbing and the reference. You can see that the path length is bent, and that allows us to have a longer path length, and so we get a much better measurement of CO2 and water vapor, but keep the analyzer to a small size. And here you can see the analyzers stacked on top of each other. The sample analyzer is on top, the reference analyzer is down below. Because we have two different analyzers, we need to have a way that we can match their readings. So that is what match mode is. Here you can see the normal flow path, and when we put the instrument into match mode, what happens is that air that normally flows out, joins with the reference, and gets exhausted, it actually gets diverted through the reference analyzer. So while in match mode, the sample air is going through both the sample and the reference. The advantage of this is you can do this when you have a leaf in the chamber. As long as your conditions are somewhat stable, you can match at any time. It is important to match when you first start. It's a good idea to match when you're working with really low photosynthesis rates or low transpiration rates. If you've changed your flow rate significantly, it's a good idea to rematch. Or if you've changed your CO2 concentration significantly, it's a good idea to rematch. And if your temperature changes dramatically, it's also a good idea to match. In general, we recommend matching every 20 to 30 minutes throughout the day. Now let's talk about chlorophyll fluorescence. Again, as a reminder, with fluorescence, we're really assessing the light reactions of photosynthesis, which we know that the light reactions and the light independent reactions work in concert with each other. So even though we're measuring mainly the light reactions with fluorescence, because those systems work in concert with each other, we really can get a pretty good idea of how the whole system is functioning. So as a review, when light is absorbed by a photon, when a photon of light is absorbed by a chlorophyll molecule, we know that that molecule gets excited, and that molecule can use that energy for three pathways. It could pass that energy to another chlorophyll molecule and eventually make it to a photosystem, photosystem 1, photosystem 2, and be responsible for electron transport. Or it could re-emit that energy as heat. A third path that energy could take is actually re-emitted as light, and this is kind of a longer wavelength of red light coming out of the leaf, and that's called fluorescence. Because we know that the excitation needs to take one of these pathways, we can develop an expression where we look at these the proportion of energy going to these three processes. And for simplification, we can drop the phi's and just talk about F is fluorescence, H is heat, and P is photochemistry. Without going into a lot of the details behind PAM fluorescence, suffice it to say that we use the fluorescence signal in a number of different moments, and we can actually estimate the amount of heat and the amount of photochemistry just based on changes in the fluorescence signal. There's definitely more details that you can research on your own, and we have more details in the manual. So the basic expression to look at the amount of energy going to photochemistry is this expression here. We have FM, and FM is the maximum fluorescence we measure during a very brief saturating flash of light, and we compare that to the fluorescence just before we gave that saturating flash of light. And we look at that difference, and then we normalize it to the maximum, and that's basically the proportion of light going to photochemistry. We can look at this in a completely relaxed, dark adapted leaf or in a light adapted leaf. And over here you can see the basic fluorescence traces, what they look like. You can see in a dark adapted leaf, FM is much higher than in a light adapted leaf. FM prime is much lower. And you can see that the FS or F naught, they are proportional to the light that you're giving the leaf. So you can put it into different states and measure these other processes. If you measure 5PS2, you can actually use it to calculate electron transport rate. You do need to know the light incident on the leaf, I, the absorption, so how much of that incident light is absorbed by the leaf, and then how much of that leaf, how much of that light is absorbed by PS2. And if you have that information, you can calculate ETR. The basic fluorometer design looks like this. It's a special chamber. It has a round aperture that's 2 square centimeters. It comes with an extra cable that connects to the console. On the cable you'll notice indicating LEDs, which are helpful to know what light is on in your chamber. You also have a pin out here where you could connect up an oscilloscope if you wanted to look at the raw fluorescence. A few basics to keep in mind is that if we have a higher fluorescence emission, we get a better signal to noise ratio. So one of our ways to optimize the instrument is to try to get as high a fluorescence emission as we can. To get that higher emission, we can either increase our intensity or we can increase our frequency. So those are two parameters that you can modify when you're setting up the fluorometer. It's important to remember that most of our fluorescence parameters we're interested in are ratios. They are unitless. If you want to combine parameters that are collected at different times, it is important to make sure you set up the fluorometer the same way. And we can talk about that in just a little bit. So a couple of the settings that you need to think about when doing fluorescence measurements. The first one is your measuring intensity. So this is the modulated light that excites fluorescence. When you're working with dark adapted leaves, you want to make sure that the modulated light does not start driving photosynthesis. You want to make sure the leaf stays in a completely oxidized or lax state. So we want that light to be very low so that it doesn't excite the photochemistry. However, we don't want it to be so low that we don't have a good signal to noise ratio. You want to look at your fluorescence trace when you turn on your modulated light on your leaf, and you want to see it come up and plateau very quickly. If you notice behavior like this, that's a sign that you're starting to drive photosynthesis. We do offer a program in the light source calibration menu that allows you to try to optimize your fluorescence intensity or your measuring intensity for a whole bunch of leaves that you want to try. Another setting that you can adjust is your saturating flash. You can adjust the length as well as the amplitude, the intensity. The length, typically you would want to keep it between 1/2 second and 1 second. And for the intensity, you want to make sure that you're saturating. And so the best way to do that is to give a saturating flash and take a look at the data. You want to see the fluorescence come up and have a good plateau before the light goes off. The pink one is an example of one that is just not bright enough, or sorry, it's just not long enough. You can see the fluorescence is starting to come up, but the light goes off before you've really hit that maximum. The blue line here is an example of one that's just not bright enough. You need to, if you continually apply another saturating intensity higher and you're still getting an increase in fluorescence, then that's a sign that the light level in the instrument is not bright enough to fully saturate your plant material. If that's the case, we have a technique called multi-phase flash that allows you to assess your maximum fluorescence at infinite flash intensity. And basically you apply a flash that looks like this. It has 3 different phases that you can adjust, and the data from the ramp of intensities, the second phase, is plotted on an inverse to the light intensity during the flash, and you can see it's a very linear response. And if you extrapolate that back to the y-axis, you can actually calculate how much FM prime would be if you had an infinite flash intensity. We have more details in the manual, and there is a paper that discusses the technique as well. If you need to do dark adapted measurements, it's always best to do these pre-dawn, where you've allowed a full night of relaxation. If that's not possible or practical, we do offer dark adapting clips. These are paper with metal springs, and these shutters pull out to reveal the leaf when you're ready to take measurements. Typically it requires about 20 to 30 minutes to dark adapt. We also, another tip would be aluminum foil works really well as well. However, when you are going to take off the foil, you typically do get some light that flashes on the leaf, so you may have to wait a little while the leaf is in the chamber before you take your measurement. Another couple of parameters require determining F0 prime. We do have far red light available in the fluorometer, and the basics are to turn off the actinic light, or the light driving photosynthesis, and if we preferentially apply far red light, it is absorbed by PS1. And the thought is, during that brief period of time, any electrons that are left in the primary acceptors of PS2 will be pulled over to PS1. And then this system will be in a dark adapted state again, and we can measure F0 at that point. So you can see you can adjust a number of the parameters, the pre-time, post-time, how long the leaf is in the dark. A is an example of a good dark adapting flash, or dark adapting pulse. You can see that the actinic light turns off, the far red light's on, the far red light turns off, and fluorescence comes to a minimum. This one is an example of one that's just too short. There is another alternative method to calculating F0 prime, and I'll let you read more about that on your own. Before we leave, I wanted to spend just a little bit of time talking about a couple of other key parameters that are available in your data file, and some things to keep in mind. One of the big parameters that a lot of researchers are interested in is stomatal conductance. And if you know stomatal conductance, you should be able to calculate CI. And both of these are in your data file. And then we'll also talk about photochemical quenching and non-photochemical quenching. So to calculate stomatal conductance to water, we have to visit a model. And here we apply basically an Ohm's law analogy, where if we view the movement of water out of the leaf, water has to move through the intercellular air spaces, through the stoma, through the boundary layer to get out into the well-mixed air. And these can be viewed as resistances to the flow of water. So we can see that here. Total resistance is equal to boundary layer, stomatal, and in the case of CO2, we would also have mesophil resistance. If we have transpiration, we can view transpiration in terms of Ohm's law, where we have current equals voltage divided by resistance. So in the case of transpiration, our voltage is our water vapor difference between inside and outside the leaf. And we can solve for the resistance to water. And if we know the resistance to water, we can calculate the conductance to water. So that's what we do here. To understand what the full conductance, what we want is the stomatal conductance to water. So in order to solve for the stomatal conductance, we have to subtract out the boundary layer conductance. So this is what the final expression looks like. We know what the boundary layer conductance is because we have measured it with wet filter paper in all of our chambers that we manufacture. We have changed the fan speed in the chamber, and we've actually measured what our boundary layer resistance or boundary layer conductance is. And so we have a table that the instrument uses to pull the right boundary layer conductance. So we know what our total conductance is. We subtract out our boundary layer conductance. We know what the ratio of stoma is from one side of the leaf to the other. And then we can calculate what our stomatal conductance is. If we know our stomatal conductance, we can use it to calculate our conductance to CO2. And here you can see that our conductance to CO2 is proportional to our conductance to water. And if you continue to follow through the expression, we can rearrange this final expression to solve for CI. So in order to get to CI, we actually use information from water, our water conductance, and our boundary layer conductance, and so forth. So when you're troubleshooting your data, you need to keep that in mind. Now switching over to some popular fluorescence parameters, they're QP and QN. And I just wanted to mention that for these parameters, it's important to be able to combine dark adapted measurements with light adapted measurements. And so in this situation, you want to make sure that you are keeping the fluorometer settings the same between when you do your dark adapted and your light adapted. And make sure that there may be data in your data file that is calculated and is showing you QP, it's showing you QN. But if you have not actually properly measured these fluorescence parameters, then the data is not going to make any sense. So it's important to be able to just keep in mind what data is in your data file and whether it relates to the leaf that you're measuring. So again, just to reiterate, because you have a parameter that's in your data file, it does not mean that it's meaningful. So you're the researcher, you know the experiment you're doing, and you have to make sure you set up the instrument to collect the parameters that you're really interested in. So there's a lot more that can be said, and there's a lot more detail in the manual, as well as additional videos that we have available. And of course the literature has a lot of advice on how to use gas exchange and fluorescent systems, and be able to assess the parameters that they're interested in. We do offer a variety of chambers for the LI-6400. You can see a lot of those pictured here. We also have a soil respiration chamber that you can purchase as well. And then just finally, we do have a newer photosynthesis system, the LI-6800. It was introduced in 2016, and it has taken a lot of the strong fundamentals of the 6400 and even improved on a lot of those features. And so feel free to go to our website and you can read about what's different in the instrument. And that's a basic overview of the theory behind the LI-6400. We have additional videos on our support site, so please feel free to check those out. Our manual is also available there for download. And if you have any questions that you need additional support with, feel free to reach out to our science and support group, or you can contact your local distribution partner. Thank you.